Jambo tena. I think now we can continue with pressure. Today we are going to have the Pascal's principle. And here is the Pascal's principle. Uh, it states that pressure applied at one part in a liquid pressure applied in one part of a liquid is transmitted equally to all other parts of an enclosed liquid. Therefore, this one tells us that for us to have Pascal's principle to exist, for us to have Pascal's principle to exist, we have seen that it states that pressure applied at one part of a liquid is equally transmitted to all other parts of an enclosed liquid. In short, the last part of the statement, which says that it must be enclosed, it means that this is a condition that is necessary for this equal transmission of pressure. We can have a look from these diagrams here, where we are trying to demonstrate the Pascal's principle. If you look at the first diagram, you can see we are having, you can say it is designed like a round bottom flask, but we have on the neck, we are having a piston. We are having a piston here. And then we have some holes. So the moment this piston will be pushed inwards, then at this part of the liquid, that is where it is going to exert some pressure. But now, because the liquid is enclosed, then we are going to have the pressure equally transmitted. So now, if you check the second diagram, the person is trying to press the neck of this balloon. Maybe it is having, we can say this one is just a balloon like. And then now it is having some liquid inside. Then some holes are made. And then the person presses or tries to tighten up these parts by pressing it. Then the liquid will come out in all direction, provided that there are some holes. So the explanation here, when the piston is pushed in, the liquid, which is for this case is said to be water, will jet out, or it will come out of the holes with equal force. So the moment one side of the liquid has been pressed, meaning that pressure has been applied, then it is equally transmitted to all other parts of the liquid. We can move down to the applications of Pascal's principle. And in this case, we are having several of them where we have the hydraulic press. This is the first one, the hydraulic press. It is used to compress textile products like blankets for packing. So you know that blankets occupy a very big or large space. Then they are being compressed using hydraulic press. We have number two, which is hydraulic lift, and this one is used to hoist cars in garage. You can see we have one part where we have some pressure being applied, and then it is going to lift a car in this manner. We have the hydraulic brake system. This one we shall look at it in detail because it is highly tested to give around 4 marks. In case it is asked, these two, they inform calculations, involve calculations. Therefore, we can now proceed and have some examples of these. Therefore, I'll say, let's have some examples. Example one, allow me read one for you. This is an example. That's an example. Be patient. Yes, now you are told that this is now a diagram. Then the Lord here, we can say it is like weight, or we can say it is like force. Then the moment there will be an application of force here, it is going to exert some pressure here. And because the fluid here or the liquid is enclosed, then that pressure will be equally transmitted by this enclosed fluid to this other arm where we are having our area 2. Then this one will lift up. It is going to lift up this load. Therefore, in conclusion, you can say pressure in arm 1 and we call this one to be 2. So pressure in 1 is equal to pressure in 2. We know that pressure is given by force over area. Therefore, pressure in arm 1 will be given as the force F. Let's try to specify it to be force 1. And we say this one is force 2. Force 1 over area of 1 is equals to force 2 over area 2. This is the summary of all this. But now, suppose now we say that force 1, the B said that it is 2 newtons, area 1 to be 3.0 square centimeters. Force 2, we are being asked, and then area 2, it be 18 square centimeters. Now we can solve. It's like now we are being asked what will be the weight, or what will be the load that can be lifted up by this setup. Then you just need to go straight and say that F1 over area 1 is equals to force 2 over area 2. And in this case, you are supposed to use SI units. Work with SI units. Then we substitute that 2 newtons divided by an area of 3 square centimeters. You can convert it into square meters by divided by 10,000, like that, is equals to our load, which is our force 2 that we're looking for, over 18 times 10 raised to the power negative 4. This is like divided by 10,000. This one, for those who don't go for the long way, want to be very simple, can say 2 divided by 0.0003 is equals to F2 over 0.00 0 1 8. One zero is not supposed to be there. So it becomes 0.018, like that. Then now we can solve. So 2 divided by 0.0003. This one you get is equals to F2 over 0.0018. If you don't want to use this one, you can work it like you say our F2 is equals to 2 times 0.0018 divided by 0.0003. And here we are going to get just a minute. You arrive at 12 newtons, like that. So what does this one tell us? This one is bringing out to us that we apply a small force effort to lift a large load or weight. That is just a working example. Now from this, we can look at the hydraulic brake system. I've said that an explanation for this one brings an explanation of 4 marks, no shortcuts, but you must get it. Therefore, allow me show you the hydraulic brake system. Here is the hydraulic brake system. You can see it clearly from my side. And then the way it is looking like, we all have the brake pedal. It is on that side. We have the master cylinder. We have a tubing, this one. We have the slave cylinder. We have the brake lining. we have the return spring, we have the drum, we have the brake shoe. Therefore, we can go to the explanation where when a small force is applied on the brake pedal, now we are talking of you apply some force on the brake pedal. Then what will happen? It pushes the piston of the master cylinder inwards. So if you want to avoid this, you can say when a small force is applied on the brake pedal, it exerts pressure on the master cylinder. It exerts pressure on the master cylinder. This produces a pressure. Now this one that we are talking of produces a pressure that is equally transmitted. Remember, we are using the Pascal's principle. It is equally transmitted to the other pistons, or we can just say it in this manner. When a force, can describe it as a small force, is applied on the brake pedal, it exerts pressure on the master cylinder. And you can say this pressure is equally transmitted by the brake fluid to the slave cylinder. So now we are now in the slave cylinder. If you look at the slave cylinder, well, then it is appearing to be in this manner. Now this is the slave cylinder. Then now, since the pressure has been applied in this way, then we expect that this piston, the slave piston, to be pushed outwards. To be pushed outwards. Can continue. The pressure generates a force which pushes the pistons of the slave cylinder outwards. The pistons then push the brake shoes and therefore the brake lining outwards. So if you have to continue, you can say we can say this opens, this pushes the slave pistons upwards. Pushing the brake shoes. So we are at this point now. This is our brake shoe. So once this one opens up, we are having our brake shoe like this. So now once this one moves outwards, it is going to open up the brake shoe. We can see what happens next. And therefore the brake lining outwards. And therefore the brake lining outwards. Once it pushes the brake lining outwards, what happens? Now, this is the brake lining. It is going now to press against the drum. And now the drum is the one that is rotating because it's the one that is of the wheel. Then it is going to slow the motion of the wheel. Pressing against the wheel drum. Thus slowing down the rotation of the wheel. That is how it is like. Those are 4 marks. And remember, there are some key words that must be mentioned in this one. One, the must talk of pressure that is equally transmitted. Before we come to that, we have pressure exerted. These two are very important. They are very important in your presentation. They are very important in your presentation. Now we can move on and look at the properties of the liquid that is being used. So now we can move on. That's the properties of hydraulic liquid. Properties of hydraulic fluid. Number one, should be incompressible. Should be incompressible. What does it mean? That no matter the kind of force or the pressure that will be applied, then the intermolecular distances for the liquid should not change. Number two, should not corrode the parts of the system. Should not corrode parts of the system. Then the last one, should have low melting point and high boiling point. You can still try to feature all this with some better explanations. We can see the first one, should not corrode parts of the system. And you can see that water is not used. Why? Because most parts of the tubing is made of iron. And iron will undergo some rusting. Therefore, if you use water, then automatically it is going to have some rusting. Now we have, it should be highly incompressible. Should be highly incompressible. What does that one tell us? At the moment you try to apply so much pressure, then it's not supposed to be changing. This brings about equal transmission of pressure. It brings about equal transmission of pressure. It is in this case where you can be asked, explain why. If you're having a bubble in a brake fluid, what could be the effect? Explain how this one can bring about, uh, or how can it cause an accident? In fact, let me launch the question. Where you can say, explain why in case of air bubbles in the hydraulic brake system can cause an accident. Explain how this one can cause an accident. So we know that air is compressible. We know that air is compressible. Therefore, it brings ineffectiveness in pressure transmission. Hence, cause break failure. Just need to, then you finish by causing extent. That is an application question from the second factor or from the first factor that it should not be, should be incompressible. Then it is wrong. I say it is wrong to say one should not be compressible compressible. Why? Avoids negative responses. Because the next time you just need to forget and include the term incompressible here, and you have carried with yourself the term not. Then you are going to miss the point out. We may proceed. Should have low freezing points and high boiling points. The purpose of this one, heat produced during breaking may vaporize the fluid, and fluid may freeze at low temperatures. So now we have been given an elaborative reasoning. Now we can go to atmospheric pressure. And what is atmospheric pressure? Atmospheric pressure. What is atmospheric pressure? Remember that here on Earth, we have what we call air column. And you can say this is now the space, and this is the atmosphere. So we expect this air because it is a fluid. Through the process of hydrogen to exert some pressure on Earth, and that is what we call now atmospheric pressure. Therefore, we can say atmospheric pressure is the pressure exerted on Earth's surface due to air column. Due to air column. We can try to demonstrate this. can try to demonstrate this. So as you can see from the diagram, these air particles will exert their own weight on Earth. And this is the one that is going to cause atmospheric pressure. Then demonstrating this one using the crashed can experiment. Demonstrating ATM pressure using the can experiment. Then in this case, you are told that pick a can like this. Then you add boiled water and you leave some space like this. That is boiled water. Then after some time, and after you're done with filling the water, you cook. Now you cook tightly. Then after this, you pour cold water. So, number one, we have boiled water. And we have cold, sorry, there is a slide. Water. Then now, once you pour the cold water, now you need to see what is going to be observed. What will be the expectation? At long last, you expect your can to crash. And now, this is the most crucial part that we need to understand is explanation. Therefore, the purpose of pouring the cold water, so you can say after cooking tightly, pour cold water. And remember, the purpose of the boiled water is to create some steam. So now you can say this one creates, or you can say forms steam. So the cold water is to condense the steam. So you can also have it here. So the purpose of this one is to condense the steam. Like that. So now, after the steam has been condensed, then it creates what we call a partial vacuum. To condense the steam, creating a partial vacuum. And what does the vacuum mean? A region of low pressure. A region of low pressure. Then now, higher atmospheric pressure will crush the can. Since we are having low pressure here, then the pressures will try to balance themselves, crushing the can. Therefore, higher atmospheric pressure crushes the can inwards. And now we have fully demonstrated the atmospheric pressure. Here it is. So in case you want a better view of all this, you can pause at these junctions so that you can see for yourself like that. You just need to pause at your video so that you can view it better. Let me try now. I think now it can be clearly be seen. Then now we can continue. We still have to look at some more things that exist to show that we have pressure, which is called atmospheric pressure. For example, if you put water in a glass of water and then you put a card on top of it, it shows that there is no space left. And then you invert the glass. Then you will see that the water will not be coming out. Why? Because there will be some resistance due to atmospheric pressure, like that. Atmospheric pressure is also the one that enables us to drink using a straw. So the moment we suck the straw, then we make the air inside the straw to move at a higher velocity. This one lowers the pressure inside the straw. Therefore, high atmospheric pressure forces the liquid up the straw. We still have the action, the one that is helping us to get drugs, liquid drugs into the syringe. The same scenario happens. So the moment you pull out the piston outwards, you lower the pressure inside the syringe. Then high atmospheric pressure will force the liquid drug into the piston. We have this sucker. When the sucker is pressed into a place, the air inside is forced out. As a result, the pressure inside the sucker becomes very low. Then it is held in position by the high atmospheric pressure on the outside. We have measurement of atmospheric pressure. We have the issues to do with the barometer. Then there is a point where we need to compare why is it that we cannot use water as a barometric liquid, but we do encourage ourselves to use the mercury as a barometric liquid. The difference comes here is as a result of the density. Mercury is about over 13 times dense than that of water. Therefore, it brings a low column compared to the water. We can give out some examples from the scenarios that we have learned. Therefore, I can give out a question which says, a diver is 15 meters below the surface of water. Determine the total pressure acting on him given that atmospheric pressure is estimated to be 100,000 Newton per meter squared, while G is 10 newtons per kg. So total pressure will be given by the pressure due to the water column plus atmospheric pressure. So in this case, when you are just given water and the water is not specified, we do take that the density of water to be 1,000 kilograms per cubic meters. Therefore, we can say the height due to water is 15 meters times 1,000 times 10. Then this one you need to add 100,000. This becomes 150,000 plus 100,000. And this is a total of 250,000 Newton per meter squared. You can still have another example which says that the pressure at the bottom of the mountain is recorded as 74 millimeters. Sorry, I can say 740 millimeters of mercury, while the pressure at the top is 600 millimeters of mercury. 600 millimeters of mercury. Uh, then be told, given that the density of mercury is 13,600 kilograms per cubic meters. Density of air is 1.25 kilograms per cubic meters, and the gravitational force, gravitational pull is 10 newtons per kg. Determine the height of the mountain. Determine the height of the mountain. This is just an application question. Then you can solve it. Very fast. In this case, you just need to say the pressure difference will be the same as the pressure due to air column. So to elaborate this, we can say that this is the mountain. So at this place, we're having 740 of mercury, and at the top we have 600 millimeters of mercury. Then we have now the air column. Now from the air column, it is the one that is going to give us the height of the mountain. Therefore, you just need to say the higher pressure at the bottom minus the pressure at the top, which will be 740 millimeters of mercury minus 600 millimeters of mercury. But in this case, you can say height 1 minus height 2 multiplied by density times G will be the height of the mountain times density of air times G. This is density of mercury. Therefore, I can say 740 minus 600. This is the same as 0.74 minus 0.6 meters times 13,600 times 10 is same as the height of air times density of air, which we have said it is 1.25 times 10. Therefore, this becomes 0.14 times 13,600 times 10 is equals to 1.25 height of air. Therefore, height of air will be given by 0.14 times 13,600 times 10 divided by 1.25, and we do expect to have we are going to get a very large number here. Let me recheck. 0.14 times 13,600 times 10 divided by 1.25. Going to get 15,232 meters. And this becomes the height of the mountain, height of air column, and this also is the height of the mountain. That is the height of the mountain. Get also one application. Where you can be having a diagram like this. So this is gas. And you can say we are having something like water here. this is open, so we expect atmospheric pressure to be acting. Like that. Then now you can be asked, if you are given that density of water is 1000 kilograms per cubic meters, we say that the height due to water column here is 5 meters. Height of water is 5 meters. We say that ATM to be estimated as 103,000 Newton per meter square. Then now you're asked, determine the pressure of the gas. And it is in this case where we need to say that pressure due to gas Tg will be given by height rho g, this is pressure due to water, plus atmospheric pressure. And this one will be 5 meters times 1000 times 10 plus 103,000. This is 50,000 plus plus 103,000. And this gives us 153,000 newtons per meter squared. I can give the final example, which is also giving some trickiness to know at what time should you say it is plus ATM or it is ATM minus. So now you can have the second case. The second case is like this. You're having some trapped air in a U-shaped whatever like this. So yeah, this is dry air that has been trapped there. So in this case, we expect atmospheric pressure to be acting in this direction. But now, this is mercury. So we are given that density of mercury, as 13,600. And then we have the height of mercury as 25 centimeters. We convert this one into SI units, which is 0.25 centimeters. And then now we estimate that our atmospheric pressure to be 105,000 newtons per meter squared. Like that. Then now you be asked, what will be the pressure of the dry air? Like this. So in this case, if you look at the atmospheric pressure, it is acting against the mercury column. It is acting against the mercury column. Therefore, you are expected to understand in which direction is the atmospheric pressure working on, and in which way should you say, is it plus or minus? For example, in our case here, atmospheric pressure is moving in this manner. Then we have mercury is moving in this manner. Therefore, we do expect them to be countering each other. Therefore, we expect each to be countering each other. Therefore, we can first calculate the pressure due to mercury, which will be hydrogen. And this will be 0.25 times 13,600 times 10. And this will be 0.25 times 13,600 times 10. This is 34,000. We continue. So now, if you look at the scenario the way they are here, the atmospheric pressure is greater than the pressure due to the mercury column. And then they are acting against. They are acting against. So this one is greater. And this one is lower. Then we'll finally say that pressure of air is given by the atmospheric pressure minus pressure due to mercury column. And this will be 1 of 5,000 minus 34,000. And you're going to arrive at 71,000. per meter square. Kindly do subscribe. If you enjoy the lessons, keep sharing to other friends, and may God bless you.